Last time I was discussing, I had very little time actually, so I just started discussing gradient adaptive lattice, but I just only mentioned what it is, so I could not discuss it at all. So, I take that up today. Okay. First, let us consider the original lattice filter, any stage, pth stage. Okay. This is the thing, this we are familiar with, but to construct this lattice we must know only one thing, that is Kp, and Kp I am assuming it to be real. Okay. For the time being, let us assume that we are dealing with, as far as this gradient adaptive lattice is concerned, let us consider only the real valued random sequence, and therefore, all the correlations, variances or correlations and all, they are all real. Okay. So, that is why Kp originally it should be Kp and Kp star, but I have made it Kp and Kp. Okay. No conjugate, because we are considering only the real case. So, then Kp was this, we all know, n minus 1 divided by any of the two, both are same, EPFN square or EPBN minus norm square, this is Kp. So, you need to construct this particular lattice stage, you need to have Kp, and Kp means you need to know the correlation between these two prediction errors as given in the numerator and variance of any of them as given in the denominator. Now, if it is stationary and the statistics is known, you can eventually get all these things in terms of the correlation of the original process x n that we have seen. We can recursively update this norm square, and also using the predictor coefficients you can evaluate this numerator thing, which I called as delta p. So, essentially giving the statistics correlation values, autocorrelation values of the original process x n, the input, the very first stage input x n, you can find out this Kp, right. But suppose you do not know those correlation values, or is slowly changing with time statistics. So, therefore, you need to have mechanism by which these multipliers they learn their value, they adjust, they adapt themselves with time, so that they finally, I mean, they learn from the data and adapt their values to the ideal Kp. So, that if the input statistics changes afterwards, it will again track and readjust itself to the new set of Kp values, that is adaptive. So, I want to make it now adaptive. When the input statistics is given, input is stationary, statistics not changing, and also correlation is known, you can calculate this. But when the correlation is not known or it is changing with time from time to time, then you have to have adaptive mechanism by which the multipliers learn, they adjust their values in an iterative manner, iterative in time, so that they finally converge on their optimal values, at least in mean, as we did in LMS case. And if there is a subsequent change in the input statistics, there is the autocorrelation values change, it will again track because it is adaptive. Okay. So, we want to march towards that adaptive version of this lattice now. We know their original values. Now, before I do that, let us see something. What is EPF? This quantity, what is this after all? X n minus the projection. Okay. Let us for the time being concentrate on this projection. Here, for this projection, this is the subspace. This you decompose as orthogonal span of what? What is the last guy in this? W1 to P plus 1. What is the last guy? X n minus P minus 1. I take that out. So, it is what I am left with is W1 comma P, and the last guy is projected orthogonally on this, and that error is taken. So, that is an orthogonal decomposition. That error, as we have seen, is EPB n minus 1. This is the span of that component, right? This we have seen earlier. That is why I am just going back to the simple derivation. Let us just try to recall how we derived. This total subspace was decomposed as what? W1 comma P, and the last element was projected orthogonally on this, and the error taken, that was EPB n minus 1. So, span of that and span of this, they are mutually orthogonal, and there is a direct sub decomposition of this. Then I projected x n on this space, means projection on this and projection on this, isn't it? Orthogonal decomposition, that is what I did. So, this P 1 P comma P plus 1 x n is nothing but projection of x n on this space, projection on this, we add the two, and then add the two, and then you subtract from here. That is how we got the lattice stage. Do you remember or not? We got it that way, isn't it? That means, what we did there was P 1 P x n plus this component. In fact, this was just Kp. I called it Kpf, but later I showed that Kpf and Kp and Kp star, they are I mean the other thing, they are conjugate of each other. In this case, they are same. So, Kp times EPB n minus 1, and then you subtract from here. This is repetition, mind you, but still I am doing it for some reason. I want to go back to this derivation again. What we did? You have to subtract, so it becomes x n minus this, which is EPFN minus this quantity, right? Geometrically, try to see this. I mean, I am not making use of any geometrical features, but just to have clarity as to what is happening. Suppose we have a situation like this, that this line, it corresponds to a subspace. Anything on this line, this is origin. This line is a subspace, isn't it? Suppose this line linears W1 comma P. This is indicated by this, and you had got this fellow, the last component. What we will do? You will project this on this space and take the orthogonal this way. So, that is this. This is the axis. This is this component. So, anybody projected on this plane will be what? The projection will be summation on of the projection on this and projection on this, because there are. But I am not making use of any angle and all that in my derivation, just inner product and all, but just for presenting it, I am just showing a figure. Okay. Now, suppose that external fellow x n is this guy. This is your x n. Unfortunately, in a 2D plane, I cannot show 3D things. You have to use your imagination, that this is actually lying outside. Okay. And this have to project on this. The plane spanned by this fellow and this fellow, or equivalently this fellow and this fellow, right? So, that will be what we all know from basic projection. That will be like, if you project it, this is that orthogonal projection. This is the projection, this is the corresponding projection error. This error is this EP plus 1 Fn, and this is that projection. This projection is given by this guy. But what is happening is, what we did here, we wrote that projection as a summation of two projections, projecting this along this error, which is this component, projecting this along this, that is, this projection will be nothing but, if you draw a perpendicular this much, and if you take a projection on this, this might become little clumsy. Sorry, this is say here, suppose this is here, this is 90 degree, then these two projections, these two fellows, this fellow and this fellow, they added together will give you this much, isn't it? That is the projection. Are you getting me? Incidentally, this component is also orthogonal projection of this fellow, this final projection. If you take it, project it on this guy, you will get the same this much component, because after all this component is what? Total x n minus this error. So, this means x n minus error, inner product with this will be what? This vertical component and this will go, second inner product with this divided by norm square of this into this, so you will get the same thing. So, whether you take this fellow and project it on this axis, or take the total thing x n and project it on this axis, you will get the same thing, same on that side. Okay. So, then what is this error? This error is this component, because I was so long talking of this projection. Now, the projection error means this fellow. So, clearly this fellow is what? This projection error, this fellow and this much, these two, this actually this is the hypotenuse, by the way. It might look to be shorter side, but this is the hypotenuse, this is 90 degree. Original, you see, this was the projection. This projection is a summation of, what I am doing in this diagram is nothing but, it is a geometrical description of these equations. This projection is nothing but this projection, that is this, okay. Then I take the error. Error means x n minus this projection, that is EPFN, that is this fellow, and minus this guy. Okay. So, this guy minus this guy is this error. Okay. This guy minus this guy, that is this error. Actually, this is 90 degree. So, this is the hypotenuse. Okay. So, how much is this guy? This guy is this vector times Kp, vector, this is EPB n minus 1, that is spanning this line, that times Kp. Suppose now instead of Kp, I have a any k. So, that can, if I say that suppose instead of taking up to this, I go up to this, then this error would become this much. If I go after this error will become this much. So, by varying k, this error norm will vary, and as you understand, as k deviates further and further from the optimal one, norm square of this error vector will increase. Again, if you go to the left hand side, it will increase. In fact, we can now show that it will be a quadratic function of that k, norm square of the error vector, that will be minimum only when we are talking of the projection, and this is orthogonal to this, because after all that error norm will be minimum only when it is orthogonal projection, that we have seen in the general case, right? Are you following now? So, if I take, instead of putting a Kp, I take a general expression EPFN minus some k times this, that is a general error vector. I take the norm square of that. Norm square has to be a quadratic function of k, which is C algebraically, but I wanted to give you the geometric insight. Quadratic function of k, so that it has a unique minimum when k is corresponding to this point, and as you deviate further from this point, that norm square of that error vector should increase. I don't know whether you understand. This is algebraically I can always show, but I don't like that. You should see the geometrical meaning. This projection error is nothing but this fellow, which is EPFN, minus this fellow is Kp EPB n minus 1. This is exactly this much when this coefficient is Kp, but suppose instead of Kp, I make it just some arbitrary k times EPB n minus 1. That means I am sliding along this axis, and instead of this, sometime if I take some k for which this much k into EPBN minus 1 is this much, then the error will become this, so on and so forth. And as I deviate further and further this way, the norm square of that error vector obviously will increase. You can see, you can now verify algebraically also, isn't it? So obviously it will be a quadratic function of k, norm square of that error vector, and it will be minimum only when I am here, because then it will give rise to projection. And that is what you can easily see. If I now consider a case like this, EPFN minus general k, and take the norm square, means all are real, so just square it up, and E, what will you get? Because of stationarity, you will have sigma p f square, k square term will come sigma p b square, and another minus twice k, this into this correlation, then expected value. Okay. So it will be a quadratic function of k, that you can easily see from here, but I didn't want to just write it that way, that look, I take a general k, it becomes a quadratic function. I wanted to give you this insight. But why it is quadratic? Because the more actually when you vary k, you are sliding along this axis. Keeping this part intact, you are sliding along this axis, and that is why instead of this optimal error, sometimes you can have this error, sometimes you can have this error, depending on the k you choose. But obviously from here also you can see that error norm will increase as k, deviate further from the point, and that you can verify. So that means it is quadratic in k, and it is indeed quadratic in k. Here itself you know that for there is only one unique k which is optimal, for which this norm square is minimum, that corresponds to orthogonal projection, and which mathematics also shows you. Okay. So suppose I carry out a steepest descent now, that I don't know what the optimal k is, like in the case of optimal, that adaptive filter. How did we go to adaptive filter? First we started with the optimal filter, we had expression R inverse p, and then I said suppose I don't know how to compute R inverse, or R is not okay, although R may change from time to time. Suppose I do a iterative procedure, I said the steepest descent search. So what I did, I took an arbitrary filter weight coefficients, I took arbitrarily, and for that I find out that mean square error of the output to the gradient of that with respect to the weight. Mean square error will be more and more as you deviate, as the filter coefficients deviate further and further from optimal one. So then I took the gradient and I went against the gradient, so that I reached the minimum point, that optimum point. Similar thing I can do here. Okay. So suppose in this stage I already know what is EPFN, EP. This is crucial. Please understand, books do not discuss all this. I am assuming that up to previous stage of the lattice, everything has been done nicely, optimally, without any error. So I am indeed getting the correct EPFN, correct EPBN. That is an assumption, which is actually not a very practical assumption, but suppose it is so, that previous stage of the up to previous stage of the lattice, everything is fine. But here I do not know this Kp fellow, and I want to find them out instead of carrying out instead of evaluating by the direct formula. I want to do a steepest descent business to find out. That means what I have to do, I formulate this quantity I call, when it is Kp, I know what this quantity, this sigma p f square, but for general k it is not sigma p f square, it is sigma p f square, sigma p plus 1 f square rather, sigma p plus 1, because when it is Kp, when it is this coefficient is not just k but any arbitrary, the proper Kp, then I have this difference is this, and its norm square, there is variance is nothing but sigma p plus 1 f square, but for a general k it is not so, that is the minimum norm, but general k is not, it can be anything, it can be more than that. So I give it a name, sigma p plus 1 is a function of k, say f square, I brought in k. So this is a quadratic function of k. Geometrically you have seen this quantity, this is nothing but what is this quantity, this is these errors. What is this difference, this quantity, this is either this error or this error or these errors. These are all function of k, isn't it? Depending on the k, depends, you will slide along this axis and you will get this error or this error or this error, okay. So this is overall thing is that error. Norm square is a quadratic function of k, of course, and Only when k is the optimal k, you got the minimum norm error. And here also you can see it will be quadratic function of k. And what it is actually, if you break it up, square it up and take expectation, sigma p f square minus twice k. Let me write down, instead of inner product, let me write down E p f n. This quantity I call delta p, isn't it? E p f n. This I call delta p. This quantity in my lattice was delta p plus sigma p, sorry, k square sigma p b square. I am assuming stationary process and all that for the time being, because when I moved to steepest descent from optimal filter, I did not throw a stationarity, I assumed stationarity. That is, the gradient expression came there, R matrix was there, P was there. Afterwards, when I switched to LMS, I approximated R by a very wild approximation, xn vector into its transpose, no averaging and all that. P vector was approximated by xn vector into dn, no averaging. But that is only when I moved to LMS from there. But up to steepest descent, stationarity assumption was valid and my gradient was in terms of R and P. Here also, when I go to steepest descent, stationarity assumption will be kept intact. That is why, if you square it up and take expectation in whether it is n minus 1 or n, it does not matter, that disappears here from sigma p f square, sigma p square. Okay. The only thing is it is a quadratic function. So, I know what is its gradient. Gradient of this quantity sigma, sorry, will be what I am writing here. So, in fact, I guess there is no point in writing partial derivative here, because it is a function of only one parameter k. In the case of optimal filter, had so many taps W0, W1 up to WP, and that output error variance was a function of quadratic function of each of the weights. You remember E, that norm square, there is a variance of that error in the case of optimal filter there was what? Was a quadratic function of all the tap weights W0 to WP. Since there are so many, I had to use the notation of partial derivative. Here I have got only one parameter k, isn't it? It is like a lattice stage, one term, another term. Like there I had xn, xn minus 1, it is just one component, another component, they are linearly combined, only one filter coefficient, okay, which I am calling say k. Instead of kp, kp is the optimal one, I am assuming I do not know, so I am putting it arbitrarily k, and by steepest descent I want to find out what the kp is, that is a different matter. So, you can drop this notation also, it should be d according to me. You know this difference, na? When partial derivatives come and when, so this should be according to me d. So, what is this? Obviously, minus twice k e, sorry, k will not be there, minus 2 e, and this 2k is here. So, that 2 and 2 I take common, E p f n E p b n minus 1 plus k times I wrote it sigma p b square. I am coming back to this form. I am putting them under the fold of E operator. Instead of sigma p b square, I am writing E p b n minus 1 square and putting it under E operator. That is fine. This quantity, square it up, and there is E. So, square it up E. Okay. And then little trick here, 2 E. There is a minus inside, is it? Oh, I took, yeah, right, minus, yeah, thank you. So, and then I suppose I take this EPFN common, sorry, EPB, EPB n minus 1 common. Then what I get is within bracket EPFN minus K Okay. What is this quantity? This is nothing but this quantity itself. This you can call EP plus 1 F prime n, prime because I did not put Kp here, any arbitrary k, so it is n. It will become EP plus 1 Fn when k is replaced by Kp. Okay, so it is a correlation is not, that is this quantity is replaced by this, so it is just minus 2 correlation between these two terms. Okay. Anyway, I just wanted you to see this mechanism, okay, that if you take this thing, I have told you something in advance, if you take this common, this comes out. This observation I will make use of later. For the time being, again I can switch over to this because I do not need this at this moment. From here, I can then derive one simple steepest depth equation as k I plus 1 as what? This is offline, mind you, this is not real time, offline, isn't it? Before I start using the lattice, I am just doing this offline business, like in all steepest descent, minus this minus some constant times, constant is say mu by 2. I want the 2 and 2 to cancel, mu by 2, absolutely similar thing, mu by 2 into this guy, del, not del, again d sigma p plus 1 k f square by dk evaluated at k equal to ki. Okay. And you replace this value of the derivative here, ki mu by 2. If you take this expression for derivative for the time being, I will go back to that little later. Actually, I should not have done that. That will come when I actually, that is more handy when I go to LMS from here. So, for the time being, let us stop here only and derive this. So, if we just take the derivative, minus 2 delta p. If you want to write it compactly, instead of writing so much, you can just write it minus 2 delta p and 2k sigma p b square. Okay. And then minus 2 and minus mu by 2, it will become mu. So, plus mu delta p, if I make any mistake, correct me, minus k means k equal to ki. So, ki sigma p b square. You are giving the correlation values. So, that means delta p and this also known to you, like in the steepest descent case there, R matrix and p vector are given in that process and gradient involved R and P. Remember P minus R W, something like that was the gradient. In the steepest descent business also, I assume input to be stationary and R and P were given to me, and the gradient was available in terms of the R and P. In fact, P minus R W at W equal to W I. Similar thing here, delta P and these are known to me, and the gradient is evaluated at K equal to Ki. That was evaluated at W equal to Wi. It is K at K equal to Ki. Okay. Isn't it? Now, suppose I want to now move from here to LMS. Again, I will see the procedure is very similar, absolutely similar. Then first thing was replace I by time index n, as though I am carrying out the iteration by looking at my watch and in time. Fine. You remember that is how we went to do LMS from steepest descent. I was replaced by time index n, and these correlations will be replaced by some wild estimates. Same thing. So, I you replace by n, delta p is what? I told you this quantity is delta p, expected value of these two. That means I should have several such products, for one sample times this, another sample of this times another sample of this, like that, and then I should average. That will be a good estimate. But suppose I am making a wild estimate, just this into this, that is all. That will be a very bad estimate. But suppose I replace that. and sigma p b square is coming. That is what expected value of the square of this term. So, I should have several samples of this term squared up, added and average, but again I replace that by a wild average, just square of this itself, like very much in LMS. So, delta p, suppose I replace as then from here I get the LMS version. What is that LMS version? That is K actually I should have a K subscript P because I am considering Pth stage, but to avoid complication I am not putting the subscript P also, but at the end when I give you the final expression then there will be a subscript with K, because it is only for the Pth particular stage, Pth stage of the lattice I am focusing on. Each stage will have its own defined constants, isn't it? So, actually this will be K P n plus 1. For the time being I have dropped actually that dependence on P, but when I give the final expression and all that time I will bring that subscript. So, K n plus 1 will be K n plus mu times E p f n E b n minus 1 and E p b n minus 1 square, and it is here I take E p b n minus 1 as common, something which I was doing earlier. I told you that I should rather do it in the case of when I move to LMS. If you put that delta p here, I will not do these steps anymore because I have already done it once. If you replace delta p by this and sigma p b square by this, take E p b n minus 1 as common because it is present in this also, this also. So, within the bracket what you are left with? E p f n minus k I k n into E p b n minus 1, which is my E p b E p plus 1 f n under this adaptive situation. Not ideal E p plus 1 f n, but under this adaptive situation means when the reflection coefficient is not the original one, but whatever you got k n plus 1 or k n. Okay. Or in case you do not understand, then I will write E p f n minus k n, this k n I replace by n, k n square of this, only one term remains. What is this quantity? That is in the lattice. In the lattice, E p f n, what is the lattice? In this lattice, suppose we are now in that adaptive framework. You gave these correct values, but these coefficients are changing with time in the LMS manner. So, at any time it is k n k n. So, corresponding output is what you have in this expression. Okay. That is, so please understand this slight differences, that when I write the same notation E p plus 1 f n, it is not with that optimal k, it is under the adaptive situation, that I am just running an adaptive filter now. This is the output. Like in the case of adaptive filter also, during the training phase it has not converged to the optimal one, but I am not discarding the output that time. There is still output y n of the filter out at the filter output, but what is that output? The output with non-optimal set of coefficient w n. The corresponding instantaneous output is y n. It is just that. It may converge to optimal one. I mean, when k n may converge in this process to the optimal one, and then onwards you will get this to be the actual optimal E p plus 1 f n as given by the lattice, optimal lattice we derived. But as of now, here it is just the one that you get at the lattice output with the available coefficient. Okay. But static assumption is that the two inputs are correct. The two inputs are correct. That is why their variances were indeed those sigma p b square and all those things. Okay. Now, the problem is, if I just stop there, the problem is this will say converge, from some choice of mu it will converge. Okay, though that convergence analysis I am not doing, because that is more complicated, because that has to take care of the fact that I assume this to be optimal, but this may not be the ideal one, because this also have been generated adaptively from the previous stage. The error, some error has come in, so the overall thing is much more complicated, so I will not do. But again, convergence analysis has been done by people, and they found out that for very low, mu has to be chosen in general. You have to take very less value of mu and all that. Some range also is given in a complicated expression, but it converges. But up till now, the problem is it will converge to some value, but that some value is what? Convergence will be in mean. It is not that it will finally exactly converge on the optimal one. There will be convergence in mean. Around the mean it will be oscillating, and then you have to see how much is the variance. The variance has to be suppressed by clever choice of mu and all that, as we did in the LMS case. Now, suppose I do the similar analysis, but with this guy. That time I took the norms, this fellow, okay, EP plus 1 Fn, this projection, this error, gave a geometrical interpretation, all that, it became a quadratic function of k, and carried out that steepest descent followed by LMS. So that this guy converges, at least in mean, to the optimal one. But I can do the similar thing here also, using the same projection kind of framework, only the names will differ, names will change here. Okay. This will become xn minus p minus 1, this will become xn, this will become w, 1 to p, it will remain xn w1 comma p, xn minus p minus 1, similar thing. So, there also I can carry out the same thing, I can put a general k, okay. This norm square will be, there is this fellow with a general k here, its norm square or variance will be a quadratic function of k again. So, you go for a steepest descent and then LMS, you will get another similar set of equations. So, that will also give rise to the convergence, and that k there will converge to the optimal one, but only in mean. But there is no guarantee that the two k's in the two branches will always remain same, and after convergence also will remain same. But the lattice ones, in the lattice filter I have proved that these two must be same, they are same under real case, they are same. So, that is never assured, isn't it? So, I have to generalize this business somewhat, so that it is guaranteed that in the after convergence also, if you know in convergence only in mean and not exactly on the optimal Kp, these two fellows are locked to each other. To do that, it is very simple to generalize this. You see one thing, if I replace this by Kp, the Kp by K, I take a general error like this error, take the norm square variance of that is of course a quadratic function of k, geometrically you have seen, mathematically you can see. Okay. Similarly, if it is EP plus 1 Bn, maybe I write down, we have seen this much, that suppose if you bring a general k here, general k, you take the norm square of that is of course quadratic function of k, the physical meaning, geometric meaning you have given and all that, okay, for this half. But there is a problem is from that only if I go for steepest descent and LMS, I have that problem that I will not be I will not be able to assure that the two k's will be locked to each other. Similarly, if I do for the lower half, that is this guy minus a general k times this, say some k prime, or say the two k's are defined. Let me just, even though I use the same notation, EPFN. If I here also, if I take the norm square of that will be a quadratic function of k by the same geometric understanding and algebraic expression, and you can go for steepest descent here and finally LMS the same manner. Problem was the two k's, they will even after convergence, this will be replaced by kn, this also replaced by kn or k prime n if you want to use defined notation. They will not remain locked to each other, they will not be same after convergence also, after convergence, not only before convergence, after convergence also, because convergence only is in mean, not exactly on optimal Kp. So, two guys approach land on Kp and therefore remain equal, that situation will not come, they are only oscillating around Kp, the optimal coefficient, isn't it? So, there is no guarantee. But now see one thing, if I just take this fellow with a general k, this was and I take the norm square of this, the variance of this, that I gave the name sigma p plus 1, I brought in k f square, and if I take the norm square of this, I can give the name sigma p plus 1 k b square. Now this guy is a quadratic function of k, and there is an optimal k, k optimal. What is that k optimal? The one k opt, which is same as k p. So this fellow would be a function like this, sigma p plus 1 and comma k f square. It will be a function like this. This much will be sigma p plus 1 f square, that is when k equal to k p. This will be having the minimum value, and minimum value is the variance of this. Similarly, if you plot this, it will be a quadratic function again of k. That minima will occur at the same k, isn't it? From our theory, because we know from the theory that the two kp's are same under real case. If you go back to the theory and no LMS now, proper lattice and all, okay, we know that this also will, be quadratic function, its norm variance will be a quadratic function of k, and that will be minimized at k equal to the same kp under real case, because under complex kp and kp star, but now kp and kp. Okay. So if I again take this expression and plot it, you can even work it out, you square it up and differentiate and all, you will get the same kp. Okay. Then it will again be a quadratic function of k, and minima will be under the, there is important thing, under the same k. So it could be something like this. It could be something like this. This much is your sigma p plus 1 b square, but actually these two are also same, so it should hit the same point. This figure is not correct, because even these two are same, so I should not show them to be different. K opt equal to k p, this is sigma p plus 1 comma k square with f of course, and this is the other one could be like this. Yeah, what is the problem? The other one could be like this, sigma p plus 1 k b square. Both have the minima value, both are quadratic, both have the minima value the same k. From the theory it appears, because under real both are same kp, and that k of is kp. And again, what is the minima value in this case? Sigma, there is a norm square of this or norm square of this, which are same, we have proved. That is why it is like this. But earlier in the steepest descent case, I forgot about one. I considered this, on this I did steepest descent and then LMS approximation. I got one recursive equation for Kn, okay, as I did that time, this one. But alternatively, you can do on this also. You get another recursive equation on Kn, and there is no guarantee that the two k sequences will, at least after convergence, will be same. But in the lattice, I want them to be same, isn't it? Because I know from theory that both the arms should have the same coefficient. That is not guaranteed in that separate business of, LMS updating either the multiplier of this branch or multiplier of this branch. How to get rid of that problem? Now, question is, each is a quadratic function of k. This also is a quadratic function of k. So, summation also is a quadratic function of k. That will have only one minima. So, then what do we do? Instead of taking this or this, we add the two, and that we minimize with respect to k. Okay, that is what is done. So, neither this fellow nor this fellow, but just the addition. So, that means now I am coming to the actual one. You form sigma p square as sigma p k square as sigma p plus 1 k square as f square, just addition of the two, just add the two. This function is also quadratic in k with the same minima, this you minimize. So, that means your steepest descent will become k I plus 1 as k I minus mu by 2 into evaluated at k equal to k I. Okay. And what will this give rise to? This norm square is, if you square it up, if you square up this and differentiate this guy, norm square, they square it up, e over this, what we will get actually after differentiation? This will give rise to what? D dk of will be equal to what? You can mentally, I mean, you can visualize it. There is no point in doing that. First, you take the square of this expected value and differentiate, and here also. Here we will get, in both cases, minus 2k will come out. Then E or maybe you can write in terms of delta p and all that. So, delta p minus, please correct me if I make any mistake, sigma p, huh?
K will not be common.
K will go, no? Yeah. Square it up, yes. K, after differentiation k will go, yes, minus 2. Sorry for this. Minus 2 delta p minus k square, k that delta p minus k into sigma p from here, sigma p b square, and then from the lower half again delta p, please correct me, delta p is that right, minus k sigma p f square. Is the thing, na? Am I correct? Huh? This is the thing. So, this you have to bring back here. Minus 2 and mu by 2 will cancel, it will be the plus mu into this entire quantity and evaluated at k equal to k I. But I will not stop there, I will go to LMS from here. From here, I will go to LMS, simply the same thing, actually what I did earlier, I am just generalizing. So, delta p will be approximated by and wild estimate, that is EPFN into EPBN minus 1 itself, no sample average and all that. Sigma PB square, sigma PF square will be replaced by what? This will be simply square of the EPBN minus 1, and this will be square of EPFN. Okay, wild estimates. If you put that back here, what do you get? And I replaced by n. So, k n plus 1 plus mu into, you take EPFN that thing common, you will see EPB, between these two you take EPBN minus common. So, EPFN minus kn times. So, this is another one, you take EPFN common, is it this? Between these two, this is EPF square, this EPF EPB. So, take EPF common, then EPBN minus 1 minus kn. Okay. So, this guy into this guy and this guy into this guy, this guy into this and this guy into this. This is a basic form of This is called gradient adaptive lattice algorithm. Of course, along with this you have to have the equations for EPFN and EPBN, that are those update equations. Okay. So, that the pH stage actually will be like this: EP plus 1 Fn, the simple lattice equation. These I am assuming to be correct one, minus K, and then instead of K I am calling it Kp. I told you I will bring the subscript P to indicate its pH stage. Kp Fn into, this we are familiar with. Similarly, the other half also we are familiar with. Again, I am assuming that this is correct. EPBN minus 1 is the correct one. Again, Kpn, and then Kpn given. We are given Kpn. We calculated these two. We calculated these two. We are given Kpn. Please, we are given Kpn. We first calculate these two. Then we march towards Kpn plus 1. This is adaptation. During adaptation also I continue to get these values. Like in the case of LMS algorithm for optimal filter, for that transversal filter. During adaptation also, with those incorrect weights which are under training process, you get the filter output, and using that you get the error. That error you feed back in the LMS algorithm, get better coefficient. And similarly here also, using incorrect KPs you get them. Using this you get new coefficient. Then you again use that back to filter in the next time index n plus 1. You understand? So, this will be Kpn sorry EPFN, I am making all kind of mistakes. No, EPFN, I told you, see diagonally, na, EPFN EP plus 1 Bn okay. This will converge, but usually we have to take mu to be very small. There is some expression for mu and all that, I mean upper bound, that I am not giving here. So, this is gradient adaptive lattice, simple. In the intermediate stage, I assume these two to be correct, and you are getting this, but these are not correct because not optimal Kp has come up. But still this data will be used in the next stage to update its Kps, but those training will be useless. But suppose for the pH stage the training is over and the Kps are indeed equal to Kp, or the optimal one are very close to 1. From that moment onwards, whatever is generated you can assume that to be correct, and from that moment onwards the training for next stage will become meaningful. Okay, so actually for all the stages then it will take more time. Are you understanding? So, that is all for this this kind of business. This is called stochastic gradient treatment. We basically will take the gradient of that error thing, and then this is a stochastic gradient because it is dependent on the data finally in the LMS case. It is not just dependent on constant quantities like R matrix, P vector, but when you move to LMS it involves data, and therefore it becomes a stochastic gradient because it is just taking the stochastic process and evaluating a gradient. Okay. So, this is one side of the adaptive filter where mean square error is minimized, a gradient is computed, okay, minimized by first computing a gradient, then approximate the gradient by data driven quantities, not correlation values, but data driven quantities, and then analyzing the convergence and all. But there is another side, another approach that is called recursive least squares, where it is more direct. There we do not do any, we do not evaluate the mean square value of some error and all that and minimize and all that. Rather we take, suppose you want to find out, you are looking at the error variance. So, you just take several samples of the error, square them up and average. That average will be minimized with respect to the combiner coefficients directly. That will be done with time recursively. That is, suppose you have taken 100 samples of some error E0, E1, so E square 0, E square 1, E square 2, like that you add up to 100 and divide by 100. These errors are function of those linear combiner coefficients in the filter. So, you minimize it, you get a set of filter coefficients, fine. But suppose now 101st data come in, 101st data come in. So you have to again compute the same square of error. To minimize that with respect to filter coefficients, if you minimize, you will get a new set of coefficients. Question is how to generate it recursively. That suppose I got that set of coefficients which are obtained by minimizing sum of square of errors up to 100 terms. If another term come in, new set of, in fact better set of coefficient will come up. How to obtain it recursively from the previous set? Exactly. There is no question of expectation value anywhere, not that. It's just numerical linear algebra. Okay, and it's more trickier, more difficult, but again far more interesting than this. So tomorrow, next class, we will begin with this recursively squares. Okay, thank you very much.